Welcome AC circuit students. In this mini lecture I'm going to demonstrate the use of Picotech's spectrum analyzer or frequency-based analyzer that comes with our Picoscope 6 software, and we can use on our Picoscope 2204 USB oscilloscopes to look at a high or low pass filter. Now of course we can build our circuit and we can use our oscilloscope and measure the voltage drop over, say, a load versus the input, change the frequency to a few different frequencies that would be significant given the predicted voltage divider effect we might have somewhere due to a reactive component, and get an idea of what we're doing with respect to whether or not our reactive component is resulting in high frequency signals giving us a higher signal over a load, or low frequency signals therefore being a high or low pass filter. Another way we can do this is to do what we did with resonance, and that's to use a frequency-based analysis. And I'm going to demonstrate how I did that for a particular type of real simple circuit. And I'm using my snippy tool, dragging it over here and kind of putting it on top of my Picoscope display. So this is a circuit that I built on my proto board. Obviously the sinusoidal source is my arbitrary waveform generator on my Picoscope, and then I have my 0.1 Henry or 100 millihenry inductor in series with a fairly high load. If I were to simulate this on Tina, I would use something between 10 and 20,000 ohms. In my Picoscope, I'm actually using something a lot higher, and that prevents sag as I sweep across the frequencies. So my total circuit voltage stays the same. That makes it a little easier to display. And then basically my inductive branch, which includes the load, is in parallel with another resistor. So we can do a thought experiment and just imagine that if we have a very, very high frequency signal coming out of our function generator, here our source, its current is going to flow out, and the impedance or reactance effectively of our inductor for a high frequency is going to be very, very high. So the total reactance or the total impedance, excuse me, of this branch, which includes the load, is going to be high, so we're not going to get as much current flow. Another way we can think about that is the voltage at this node between our inductor and our R1. The voltage drop between that and the other side of the load is, of course, the full voltage of the circuit, and we've got a bit of a voltage divider between our inductor and our load. So the higher the frequency, the higher the inductive reactance, and so the more voltage drop we have over our inductor versus available for our load. So from that standpoint, we would tend to think that we would have a low pass filter going to the load, where the lower the frequency, the more our inductor is going to act like a short, and the more the voltage drop over our load is going to be the full voltage being applied to the circuit. It would be as if in that case, with a very, very low frequency, it would be as if our load were basically just in parallel with R1 and seeing the full circuit voltage. The higher the frequency, the more of the voltage drop in this branch is going to be taken up by the inductor. So that's what I've built on my proto board, and I am actually, let me bring this back. So I actually have one of my scope probes, my channel A, is looking at the full circuit voltage, so I have it basically put somewhere like around here on my circuit. And then I'm also on channel B, I'm monitoring the voltage drop between the inductor and the resistor, so that's capturing the voltage drop over the load. Now, since we have a fairly large difference between those, and it's a large voltage drop total and a small difference for a large portion of the frequency sweep that I'll show, what I've done is use the tools and the math channels, and I've created a new display channel, which is the difference between channel A and B. So on our purple channel, which I've I've rescaled to a very, a very magnified scale. So full scale for my purple scale is around 100 millivolts as opposed to 1 total volt for channels A and B. I'm able to really zoom in on the difference between voltage drop over the load and voltage drop for the full circuit, since they're really the actual absolute difference isn't really all that big for the frequencies I'm sweeping over. Now, obviously, if I went out to huge frequencies where the voltage drop over the inductor was pretty much most of what I'm applying, we would see a big difference. But this is by using this difference, I'm able to show the difference that we're seeing with frequencies without having to sweep over a huge frequency range. Okay, so let's walk through the setup. I'm using a 512 bin frequency resolution, which is going to allow me to basically see just the top and kind of plot a line using the peak hold function. And I'm looking at linear rather than logarithmic. I'm not expecting to see a huge difference, so I definitely don't want to compress my y-axis by using a log scale. I'm going to use a linear. And I'm sweeping from 10 Hertz, which is practically DC. I have my sweep set to go up and down. I'm just basically going to sweep up once. I can let it run as many times as needed if I have a lot of noise to show a better signal. And I'm going to stop at 12,000 Hertz. Now, we can go ahead and pre-calculate what the actual inductive reactance would be and basically calculate a voltage divider between the inductor and the load for whatever load resistance we have. But in this way, we're just basically going to measure it because the object of this exercise is to just show whether or not we have a low or a high pass filter. Again, we could predict it, but there may be a situation where we have a more complicated circuit, and for a particular output voltage, where we were basically taking the voltage drop over some component somewhere, and we want to know what the total effect of a source frequency change somewhere remote is, we could use this same kind of technique to measure and get an overall trend. So right now I'm not collecting any signal, I'm stopped. So the first thing I'm going to do is collect a signal, and we can see little flecks of data being collected, and we can now see the difference between our scales. We've got 1 volt full scale on our full circuit, 1 volt full scale on our voltage drop over the load resistor, and then about maybe 91 millivolts full scale on our total circuit minus load resistor, our delta signal. So now we're going to start sweeping, and we can see we've got a fairly flat plot. So both the total circuit voltage and the load resistor voltage are pretty much the same. So for these frequencies, we're approaching 2 kilohertz. The inductor is not dropping a lot. But on our magnified scale, the purple line, we can see we went from 0. Now we're beginning to get a little bit, and we can track that. We had a little noise as we moved the slider there. So 4 millivolts, not a whole lot. We're beginning to see a little bit of separation. Remember, we've got a voltage drop over our load versus the whole circuit plotting together. Again, a little bit difficult to visualize here as we go along, and we're also beginning to pick up a little bit of the change in overall reactance from the Picoscope. Making sure I have everything set up the way I think I do, what I'm measuring where. So again, we're seeing some difference between the total circuit and the load, but where we'll really be able to track it is our magnified scale of that difference. And in fact, it's a positive difference as we go along. So we can basically stop this. And so from the fact that the difference between total circuit voltage measured on our channel A, our blue channel, and our voltage drop over the load resistor, if that difference is increasing, which is what's being shown by the increase in this purple plot, we can say, okay, the load resistor is getting less and less of the total circuit voltage as we go to higher and higher frequencies, which of course indicates that we have a low pass filter construction in the circuit that we showed, which is pretty much what we were thinking about in our thought experiment. So higher frequencies means the reactance on our inductor gets higher, the voltage drop over our resistor ends up getting lower proportional to the total circuit voltage. Okay, now that we've looked at the behavior of an inductor basically as a voltage divider creating a low pass filter to a load resistor in series with it in its own branch, we're going to look at what happens if we switch that inductor with a capacitor in the exact same configuration. So I'm displaying, I can't scale it up. I'm displaying basically an equivalent circuit in a schematic here. Hopefully you can see my cursor. So I have the same sinusoidal voltage source, and in the branch that includes my load resistor, I've swapped my 0.1 Henry inductor with a 1 nanofarad capacitor. So the small capacitance, it's in the denominator. It's going to give me a fairly big response as I sweep through frequency. I'm going to end up having a fairly big capacitive reactance as I go from a high frequency to a low. Of course, I'm going to sweep the other way. So I'm going to start with a really low frequency, and as I am near DC, of course, this capacitor is going to act like an open, so the load resistor is not going to really see any of the total circuit voltage. But as my frequency sweeps up, I should drop less and less voltage over this capacitor, and I should see my load resistor we should have more current flowing through that branch, and my load resistor should see proportionately a higher and higher fraction of the total circuit voltage. So I'm going to again use the frequency sweep, our frequency on the x-axis spectral analyzer, to look at that again. This time I don't need to use the differential signal. I can just plot my total circuit voltage with my channel A and my voltage drop over my load resistor with channel B. I'll make a note that I'm using a different combination of R1 and R load that basically suits the Picoscope's response better to show the signal response. But the trend in terms of being a higher low pass filter with respect to the load where it's positioned in the circuit would be the same. So I am now collecting signal, and I'm going to sweep from 10 Hertz again, practically DC, to 12 kilohertz. And so we're going to turn our sweep on. So you can see our total circuit voltage signal, channel A, is up here. And here's our voltage drop over our load. We have it scaled. They're equal scales actually, but we have it scaled such that we can see it climbing. And not surprisingly, the frequency response is effectively looking pretty linear, even though frequency is in the denominator of our reactance. When we apply Ohm's law, that ends up being a linear response. So basically, we're seeing more and more voltage drop over that load resistor the higher the frequency. And so for this particular circuit, from the standpoint of the load, we're seeing the action of a higher pass filter, meaning the higher the frequency, the more voltage is being passed to the load. So the red line is representing the voltage signal over the load. So we can turn that off. So this concludes our short demo on a way to use our Picoscope spectrum analyzer or frequency analysis tool, basically this tool right here, to evaluate frequency response of filter circuits. So this is totally analogous to what you might have done with a resonance circuit. It's just an alternative to basically picking frequencies with our oscilloscope over here, and where we could, I didn't plan to show this, but we could theoretically sweep frequencies and show that same thing over here. Running, we've got it showing yet. Maybe not scaled right. Maybe I bit off a little bit too much there, showing the sweep. Oh, we're starting too low. Excuse me, we'll go to something reasonable. So here I am ad-libbing, showing basically the alternative way of doing this. Or not. Take a pause. Okay, back from my quick pause. As you noticed, before I stopped the recording, it appeared that my arbitrary waveform generator had just simply stopped working. This is a failure artifact of the Picoscope software. Sometimes it just has a glitch. This is kind of like having your CAD program crash. So what I did while I was paused is I exited out of the program, which shut down my Picoscope automatically. And then I got back into the program, the Picoscope started, I selected my sine wave function, turned it on. I'm auto-scaling my blue channel A showing my full circuit, and my channel B showing the voltage drop over my load resistor, which is in series with a capacitor. And so I'm showing a very low frequency signal, 100 hertz. It's a little bit more than what's coming out of our wall socket, but not too much. Now earlier we showed what a frequency-based signal looked like. Now we're back to our regular scope. Time-based signal, we can use a sweep mode with our scope. One of the problems with that is it's sometimes difficult for auto-scaling over a large region for the scope to keep the trigger and the auto-scaling, both time-based and our voltage signal on the Y. And so sometimes it just looks jumbled. I find in this case it's easier to just select some frequency. So I'm starting with a very low frequency, and you can see I'm scaled up to 50 millivolts, looking at the voltage drop over my load resistor, and it's still pretty low and pretty noisy. So something like maybe 5 millivolts as opposed to 600 millivolts full scale over the whole circuit. But if I change to something moderate, 5K, and now I go and reduce my time per division because I'm at higher frequency. Now I'm at 500 millivolts full scale for my load resistor, so, and still at 1 volt for my full circuit. So now I'm dropping something on the order of 1/3 of the total circuit voltage over my load. So that right there demonstrated the high pass nature of this particular circuit, where I have my load in series with a capacitor. So I went to a higher frequency, and now the fraction of the total circuit voltage available that's dropped over my load increased. So more voltage is effectively being passed to the load, hence high pass. So that concludes our high-low pass spectrum analysis, and then with a little finish going back to our time-based oscilloscope signal with our capacitive-based high-pass filter circuit.